Well, hello friends. Welcome back to another OS haxx0ring video. Today we're going to write an exploit for a bug that was recently fixed in Serenity. So I'll show you the bug first. It was in the memory manager class here. So we have this problem that in an application that would use a lot of memory, it would eventually crash for some mysterious reasons. And it took a while, and then Tom tracked down the bug to this thing right here. And basically, it has to do with the way that we allocate and free page tables, the per process page tables in our kernel. And let me draw it out for you. So basically, there are multiple levels of page tables, and a virtual address that say that you have this address, right? We're a 32-bit operating system. So this address right here, the top 2 bits of it control sort of the highest level of page table, and then the next, I don't remember how many, 10 bits or something, control which page directory, and then there is yet another that chooses which page table entry. And then it's only really the bottom bits of an address that are an index into a physical page of memory. And so the way that we keep track of page tables in the kernel, because we dynamically allocate page tables whenever a process needs to use some new virtual memory, and the way we were keeping track of these is that we just store them with the page directory. So page directory is a per process class that manages the virtual address space and virtual to physical address mappings for a process. And whenever we allocate a new page table because we need to use some new part of the virtual address space, then we put that in the physical pages hash map here. And the key into the hash map is the page directory index, and this is really just to hold on to physical pages that are used for page tables, basically. And until recently, we never even threw these away. We would deallocate all of them when a process would die, but basically as long as the process was alive, it would keep all of its dynamically allocated page tables alive as well. But the problem here is that we are using the page directory index as the key into this hash map, whose only job it is to keep the pages alive. And you can see that here. When we're adding a physical page that we've just allocated, we're adding it to the physical pages set or hash map. We're using the page directory index. But remember what I was showing you about the addresses. Where did it go? Here. That these 2 bits right here control the highest level of the page table hierarchy, and then these are the page directory index. And we've allocated a page table, so these are less relevant. The relevant parts are here. And so the thing that goes wrong here is that we're only using this as an index or as a key in our hash map, which means that if you have 2 page tables and they have the same page directory index, but they have a different higher order index, then we're screwed because they're going to have the same index. So overwriting, it will overwrite any existing entry. And basically, my idea for how to exploit this is to just use fixed mmap. So that's what we're going to do today, and try to use this to get control of a page table and then get root access somehow. So let's see. Also, this costume is really warm, so I'm just gonna scale it back a little bit. All right. So let's see here. Maybe we'll turn the light on as well. Oh, that's a bit nicer. All right. So let's see. First thing we want to do is just verify that we can trigger the bug, right? So we'll start by just making a test program that would be something like, we'll call it haxx, because that's a cool name. So haxx, and let's see, so this is going to require calling mmap. And really the easiest way to trigger this should be to just be to use two fixed addresses that would collide in the upper 2 bits, so something like these two, right? Wait, does this make sense? Upper 2 bits. Wait, let me, I feel like maybe I'm getting this wrong. Let me look it up. Where is the thing? Or I can just look at memory manager. Page directory table index. It's the upper 2 bits. Yeah, okay. Then I guess so what does that correspond to if we just to simplify this for myself, because I'm struggling to visualize right now. Right, so that's 1 gig, 2 gig, 3 gig, and 4 gig. Those are the, or 1 gig, 2 gig, 3 gig. Those are the markers. And this one is a kernel only, so we can't map that, so we're actually stuck using these two. And also we won't be able to use the 0, because that's the null page, it's reserved. So anyway, let's see if we can just reserve something at these two. Okay. I guess, let me grab my pipes header. I didn't really fully think about how to do this, but I think this is going to work out. So we'll call it A, and we'll memory map 4,000, 4 fajillion, I mean, and how about 1 page? So that'll be 4 kilobytes, and for some reason I can't remember the mmap argument order, so that's not that. Where are you? Right here. Okay. Size, prot read, prot write. Flags can be map anonymous, map private, map fixed. So fixed is the important one, because fixed says that we want to use specifically this address. And file descriptor and offset don't matter. Okay, so if this fails, then the party's over, and then we will do the same for B, which will be mapped at 8 fajillion. Also, I don't know, my syntax highlighting is not working. I don't know why. Okay. So print mappings ready. Okay. So basically, what should happen here is that first we would allocate some virtual memory and put 1 physical page at this address. That will work fine. And it will be like new virtual memory because we haven't put anything near that address range before, so we have to allocate a new page table to manage that virtual physical mapping. That part will be fine. But when we do this call right here, then we'll end up here again, and we will overwrite the physical pages entry, this guy right here. So the physical page that was previously allocated for this page table mapping will be unceremoniously nuked from the physical pages set, and it will be deallocated and returned to the physical page allocator. So actually, we can even do something here, like you can assert that the result is hash set result. Assert that we're always inserting a new entry, because set on a hash table can return either inserted new entry or replace the existing entry. And if we get replaced existing entry, then we have just screwed ourselves. So this assertion actually should have been here maybe from the beginning. We would have caught this. So props to Tom for debugging this, by the way. Okay, so if we just run haxx, we should hit that assertion. Yes. So that's good. Now we know we can trigger the bug. So the next step is that we want to, so basically we know now that when we do this operation right here, then the physical page that was used for this mapping will be returned to the physical page allocator. And because our physical page allocator is pretty stupid, it's just gonna, like the next time somebody requests a physical page, they're gonna get the one that we just freed. That's definitely something that we should look into mitigations for going forward. But right now, I think this will be the sort of very helpful in making an exploit. So what we want to do now is we want to allocate a physical page and then put something fun in there. So I guess the easiest way to do that is just to maybe call mmap. So make a third one. And this time we'll tell him put it wherever. And page size. And yeah, same permissions really. Prot read, prot write, map anonymous, map private, not fixed. Let the kernel place it wherever, it doesn't matter. And let's see, if I'm right about this, then this should actually be backed by the physical page that was used for the page table for this mapping. And then the thing is that the reason that this is exploitable, I think, is because we didn't actually unmap that page table. That page table mapping is still there. So in the big page directory for this process, it still has the physical address that I'm about to steal here. So I think we can just put page table stuff in here and we can use it to direct access wherever we want. So let's see. Maybe let me grab the page table entry class here from the kernel. We'll just yoink that in. So that'll be easier than doing it manually. Okay, and then let's see. So now we have the page table in C. We can even rename that stolen page or hijacked page table. And then, so let's start by just clearing it out maybe. Make sure that we are actually able to do that. Memset, hijack page table, page size. Okay, and then let's make a page table entry. So the page table entry is, I guess we'll just do the very first one here. So let's see, we'll do it this way. Okay, so let's say that it's present, set present true. set writable true, why not? And then we'll set the physical page to, how about 0, like the 0th physical page of RAM. That's where we should find all of the, like the BIOS interrupt vectors. That's what they would be, so we would see a bunch of BIOS addresses if we print out the content here. So let's see. Let's just print out some numbers. How about 256 bytes? I don't know, just something. Just want to print out something. So if I and I%16 is 0, then new line, otherwise just also printf something like this. Hijacked, oh no, not the hijacked page table. So we have to read through this pointer. Hijacked pointer, or sneak peephole, let's call it. That's our peephole. Okay, and go. So let's see what we can see through this peephole if this works. Haxx. Oh, right, the assertion. I forgot. So we'll remove the assertion. And let me just remove it entirely. Okay, so we got a crash. Why did we crash? We have a protection violation error at address 4 fajillion. Is this because, oh wait, I forgot to make it accessible to user space. User allowed, true. Otherwise it will think that it's a kernel only page. Ooh, look at that. How easy was that? So these look like your typical BIOS pointers. See here we have segment foo and then offset ff53 and whatever for most of the vectors. So these are, I guess, are like the exception vectors, and then in here you find like BIOS interrupt 10H, 13H, and all of those old favorites. But that's stupid easy. So that means that we have access to a page table that we can direct to any physical page in the system. So I think we don't have any address space layout randomization in user space or the kernel yet, although that wouldn't help us here anyway because this is about physical memory, and I think the kernel is always at the same place. Yeah, here you can see that we're always just loading the kernel at the 1 megabyte mark, and that comes from the bootloader. So the bootloader always puts the kernel in the same exact location. So the same exact location physically. So let's just exploit that by patching the running kernel and giving ourselves root access, because it shouldn't be too hard now. Let's see, what do we want to do? In the past, I've used the setuid call, so maybe let's just do that. Let's see, let's look at the sys setuid. So basically, we ignore this part, or really what we want to do is we want to just bypass this check right here, because this is the check that prevents you from setuiding. And the easy way would just be to patch in a short jump from function entry to this. So if we look here in the obj dump, we can see that here is the check, safety check. Here is the branch out if you fail the safety check, and then here is where we start assigning the UID that you've provided. So we want to jump to this address from the start of this function. So I guess, how about from, we can jump from here, or we can actually here. This is good. So I'm going to jump from here. And then how long is that? 118 bytes. So then we can do like a really short jump. And I always forget what the instruction encoding is. So it's right here. Jump short M. It's EB, and then an 8-bit signed immediate. Okay, so we just patch in an EB and an offset. EB 118. Okay, we can do that. So then let's see. So we want to get this physical page. That's where we would find it in the kernel. And then we want to, so we can skip this part. And then we want to write the memory at, I guess we write through the peephole, and the address is the bottom 12 bits here. So E27 is going to be EB for jump short, and then haxx028 is going to be, what was it, 118? And then it's relative to the next instruction after. So this is 2-byte instructions, so 116. Okay, so that should patch the set UID syscall. Let's try to call it. See if we can set our user ID to 0. And let's see, so if that fails, sorry, no hacks today. And then otherwise we'll just drop a shell, right? Why not? That's the thing that you're supposed to do if you're a cool haxer. No hacks today. Crap. Alright, what did I do wrong? Well, let's see. Let's print out what's already there. See if we're looking at the right place. Pre-patch. I don't know if I did this. Probably I didn't do this correctly. Peephole. What is there? E81B. Looks like the right thing. E81B. and then I'm patching in EB116. Which, wait, let me just see, am I just doing a stupid right now? It's a short jump, sure. Let me verify this is the other way around. So from here, plus 116, actually plus 2 for the instruction, and then plus 116, and then we hex that. We should end up at E9D. Oh, wait. We end up at the jump. That's not what we want. Because then we'll bail out of the function. So we actually wanted 118. Okay, this offset math is difficult sometimes. Oh, look at that. Ah, we got root. Okay, so that was pretty easy. Man, it's this is really fun, like making these things. I guess it's probably significantly easier for me because I'm so familiar with the kernel already and all of this stuff. But I imagine it's probably really fun if you're targeting somebody else's kernel too. But this is super fun. So exciting when it works. So yeah, so we got root. That means that we can do root stuff. Go to root's home directory, and we can even do stuff like shut down the system. Cool. Very, very cool. Actually, I think maybe the normal user can shut down too. Yes, because he's in the special group. So what's something only root can do? I guess, why can't I think of what only root can do right now? Maybe add a new user, hacker. Aha! I am now hacker. Oh, and now since we're hacker, let's become root again. We became root again, and see now it had our little patched code already in the kernel. So now anyone can set UID to whatever they want. That's pretty cool. So yeah, so that's the way to exploit that, I guess, or one way to do it. So let me show you what the bug fix for this is. So let's see. So in order to make this video, I've reverted 2 patches here that fixed this issue. Really, primarily, it was this one that fixed it, and then this one improved upon it, because now we also deallocate page tables that are no longer needed. That's not something we were doing previously. But anyway, if we just, I guess, just go back to master, the way it is today. Then you can see here that we are using all of the top bits now as the key into the page table hash map. So we're no longer falling into the stupid trap of using only part of the relevant bits. And then we also have the assertion here to catch this problem. And of course, we should maybe verify that that the hack exploit no longer works. No hacks today. So that's pretty cool. So yeah, so the bug fix was this, just using all of the bits, all of the relevant bits of the address as the key for page table entry thingy in this hash map. And we should really be looking into some more mitigations for this. The way I just exploited it, the fact that I was so easily able to just get that physical page that was just erroneously deallocated is obviously a huge benefit for exploitation if you can reallocate a page that was just deallocated. So we should really be looking into some kind of delayed free or some other strategies for reusing physical pages so that they don't enter back into the system right away and make it so easy to control getting that page again. So it's something that we need to work on. And then I guess it's pretty annoying that the bootloader puts the kernel at the exact same place in memory every time. I'm not exactly sure what to do about that outside of making our own bootloader or our own sort of intermediate bootloader that goes between the bootloader and the kernel. There are a couple of different strategies, but it is irritating that the kernel is at a predictable address physically, right? And maybe there are other mitigations we could do here as well that I'm not aware of. So if anybody knows or can think of some interesting mitigations, please get in touch, because I'm always interested in beefing up the security of the system. And I am by no means an expert on security. I'm just learning this as I go, and making exploits is an important part of learning, at least for me. So I'm glad that we were able to make one today with relative ease. So yeah, so this was the video about this, and I guess I'll just say thanks everybody for checking it out, and yeah, I guess I hope to see you next time.